Hello grade 12s. Today's lesson covers notation and rules for differentiation. Now if you recall, in the previous video we looked at first principles differentiation, which takes the definition and helps you to then find the first derivative of a function. Now I did say in that previous video that we only use first principles differentiation if it's asked for. You never ever go and use first principles differentiation if it's not asked for, because it's a very long and cumbersome way to find the first derivative. So what we're going to do today is we're first going to go and discuss notation. Very important. I've already spoken about the importance of notation with limits, and I've already spoken about where that limits come into the first principles differentiation as well, where if you go and you mess up the notation, unfortunately the mathematics is wrong. So this is why we first need to have a quick discussion about the notation for differentiation before we can get into the rules for differentiation. Right, so when you go and you say if f of x is defined, and then I've just left a blank there because obviously f of x could be defined as anything. It could be fx is equal to 2x minus 3, which is a straight line. It could be fx is equal to x squared minus 2x minus 8, which is a parabola. It really doesn't matter what fx is defined as. But if fx is how they define the function, then when I go and I indicate that I'm now writing down the derivative, I use the notation f accent of x, which refers to the first derivative. So the moment they give me the function defined as fx, I will then go and I will say the derivative is the first derivative of fx, or f accent of x, and I will then find that derivative. We've seen this notation in the first principles differentiation already, so it's not anything strange at the moment. Then if y is equal to, in other words, if the function is not defined as fx, the function is defined as y. So in this case, y could be equal to x to the power of 3 minus 4. And that, by the way, we're going to learn later, is called a cubic function. So if I define the function in terms of y, then when I go and I indicate I'm now writing down the first derivative, I will use the notation dy over dx is equal to. So that's the notation for the derivative if they define the function as y. Now, this seems strange to some of you guys. And you're like, why is it dy over dx? This, I personally think, is the easiest thing in the world to see. Dy stands for the difference in y. Dx stands for the difference in x. Now, remember when we started talking about differentiation, I said to you guys, I say derivatives, you say gradients. We are finding gradients. And when we find the first derivative, we are finding what we call the gradient function. So even this notation, dy over dx, the difference in y over the difference in x, which if you think about it is the definition of gradient, indicates that I'm now finding the gradient function of y. Now, these two notations are very common. In fact, they're the most common. I will do a couple of variations on them just now, but they're very common and they're very easy to understand. Sometimes, however, they go and they say, if only an expression is given. So if only an expression is given, like half x squared, then what they will do is they will say, given the expression half x squared, please now find the derivative. And this is the only notation that some people slightly struggle with. So if they define the function as half x squared, they don't define it as y, they don't define it as fx, then the notation we use over here, and there are two notations we use. The first one I write as I say, it's the derivative, or the difference in, I should rather say, not the derivative, it's the difference in, and now we don't have a function defined as y. But I know that y is in fact half x squared. So they haven't called it y, but that's the function that I'm trying to find the derivative of. So instead of writing y, I will then go and inside my bracket, I will write the entire function. I will write that half x squared. And then just to finish this notation, I will write dx. So this reads, if you compare these two, this reads, find the derivative of a half x squared, which in this case would have been defined as y, but in this case it wasn't defined. So because it wasn't defined, I have to write down the entire function. So find the derivative of that function in terms of x, and we will talk about that in terms of x a little bit later when we're doing other examples. But you will then go and you'll write it's d over dx of that particular function is equal to, and then I will go and I will write whatever the derivative is over there. Now, another way to write this down is you can also go and you can say, find the derivative of that function half x squared in terms of x. So this is another way just to write out that derivative if the function isn't defined as fx, so you can use the f accent x notation, or if the function isn't defined as y, where you can use the dy over dx notation. So if it's not defined as fx or it's not defined as y, then you will just go and say, I'm now finding the derivative of that function in terms of x, or I'm finding the derivative of that function in terms of x, and I will then proceed to write that out. So this is the 4 notations we use. I will discuss a couple of variants of these notations, and there's also actually a little shorthand for that y notation that I will also talk about, that some of you are going to prefer much more than the dy over dx notation. Please bear in mind though, sometimes the question forces you to use a particular notation. So you don't really have an option to use a different notation. You're going to have to stick with that particular notation that the question forces you to use. So just some variations on this. The first one I want to talk about is over here. So I said if f of x is how the function is defined, then I write down the derivative, the first derivative, as f accent of x, which stands for the first derivative of fx. But sometimes it's not a function that is defined as f, and the variable that they defined, the independent variable, is not x. So the science people might recognize this. So if you don't do science, please don't worry too much about that. But the science people might recognize this as displacement time function. So S stands for displacement, T stands for time. Now what they've done there is they've now defined the function as the function of S, and they've now defined the independent variable no longer as x, but they defined the independent variable as t. And they will then go and give you a formula for that function. Now, if you want to go and you want to get the derivative for this particular defined function will just be written as s accent of t, and then you will go and you will write down the derivative. So it's really not a big stretch to go from fx to st. You just have to remember I put that little dash there, which means the first derivative of whatever function is defined. Now, I also said I was going to talk about this one, some variations of this one, and I was going to show you a shorthand of that one. So this particular notation, what they can do is they can go and they can say, instead of defining the function of y and then having x over there, which means the derivative is then defined as dy over dx, they could actually go and they can do something like area is equal to. And then, if you recall, inside that area function, so let's just put an independent variable in there, it might be something like length times something else. Okay, we'll talk about that a little bit later on. But if it's defined as length times something else, you can then go and you can define that particular one. When I write down the derivative, I can say it's dA, so it's the difference of the dependent variable a over dl, so that would be the difference in the independent variable. So instead of having y and having x, we now have a and l as our two variables, and therefore I will then go and I will find dA, the difference in a, over the difference in l, and I will use that. Now, added to this, you could have a nice little shorthand instead of using that dA over dl. And that shorthand is pretty much just saying, I want to find the derivative of a. And I can just put a little dash over there, and I can say it's the first derivative of a, and I can write it down. So that's another way that you could also have written this derivative. Instead of going dy over dx, you could have gone y dash, and then you could have written down the derivative. Now, these ones then obviously, depending on how the function is defined, might have different variations. So if you go, for instance, and you say, this is the expression that you need to find, and the expression could be something like a half, and let's use a variable of p squared. Then they would have to go and they would have to state that you are trying to find the derivative in terms of p, which is now my independent variable. P is my independent variable. Then you can't write down, I want to find the derivative of that half p squared with regard to x, because there's no x there. In this case, my independent variable is p. So I have to go and say it's the derivative of that function in terms of p. So these are just a couple of variants of that notation, but as I said, we will, when we find the derivatives, we'll constantly be referring back to these notations and how you're going to use these notations to make sure that you don't write the notation incorrectly, which then unfortunately makes the mathematics incorrect, because they do penalize you if your notation is incorrect. So please, 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 it's not that you can just do whatever you want. Notation is important because it's the difference between making the mathematics correct or incorrect. Right, so now let's look at the rules for differentiation. So if I look at the rules for differentiation, again, I want to reiterate, first principles is only used when the question asks for it. You will never, ever, ever use first principles unless the question asks for it. Now, here's the first rule of differentiation. Rule 1 says the derivative of a constant is 0. So if I were to go and say, for an example, I have a function y is equal to 3. Now, that is called a constant function because if I were to draw it on the Cartesian plane, I would simply go and say there's 1, 2, 3. It's a straight line, specifically a horizontal line that goes through 3. So that's the function y is equal to 3, a constant function. And that's why we refer here to a constant. Now, that means, according to this rule, dy over dx, which is then my derivative, is equal to 0. So the derivative of a constant is 0. Now again, why? This is important, and this is a direct result again from saying, I say derivatives, you say gradients. Differentiation is all about finding gradients. And what is the gradient of that horizontal line? Hopefully you guys know the gradient of that horizontal line is 0. And if the gradient of that horizontal line is 0, the derivative of that constant function has got to be 0, because that's what we're trying to find. We're trying to find derivatives, and that is why the first rule, the derivative of a constant is 0, is actually very logical if you refer to this graph. Right. Now the next rule for differentiation says the derivative of x to the power of n is. Now this is very, very important to understand, and we are going to practice some very basic examples on this again and again and again. So the derivative of that particular function, very simply, I do this. I take the exponent, in this case, and I write that exponent in over here, in front. And I multiply by x. And then, this is the crucial bit. I take that exponent in, and I reduce it by 1. I make it 1 less. So, listen again, the derivative of x to the power of n is n, there you go, times x to the power of n minus 1, and there's that n minus 1. Now, this is specifically based on the whole idea of derivatives again. Remember, our notation for derivatives says dy over dx. So we are finding a derivative which is a gradient. Now, if you notice over here in my notation on derivatives, I'm dividing by the difference in x. Now, if you go and you divide x's, any x with an exponent, like for instance, if I go and say x to the power of 3 divided by x, I get x squared. If I go, for instance, and I say x to the power of 6 divided by x, I get x to the power of 5. So the moment we divide by an x, my exponent becomes 1 less. My exponent becomes 1 less. And that is why whenever I find the derivative of a function, the exponent has got to become 1 less. Now, the fact that you multiply with the n in front there, that is again a direct result of the definition of derivatives, which comes from first principles. But that making the exponent 1 less, please, please, people, that comes straight from the fact that we're trying to find gradients, and because we're trying to find gradients, I need to divide by the difference in x, so the exponent becomes 1 less. Now, I just want to quickly also state something else. If you go and you look at the derivative, in this case, of a function that's defined as k times x to the power of n. So if there is a different coefficient there than the coefficient of 1, which is apparent there, then all you're going to do is with that exponent, you're going to multiply the exponent by whatever constant is already there. So I'm going to say it's n times that constant coefficient, And then again, we're going to go and say to the power of n minus 1. So this is going to be my derivative. Right. So make sure you understand this. Make sure you know exactly what I'm going to be doing, because these are the rules. Number 1, the derivative of a constant is 0. And then number 2, the derivative of x to the power of n, I multiply by the exponent, and then I make the original exponent 1 less. Or in this case, I multiply the coefficient by that exponent, and then again I make the exponent 1 less. Please make sure you've got that firmly in your head when we do the examples that are about to follow, just so you know what I'm doing every single time. Right, so some examples. These examples are very easy, straightforward examples, just to get you used to the rules of differentiation. The first one then is example 2 on page 202, and it says write down the derivative with respect to x, and that with respect to x we'll talk about a little bit later when we do different examples, because always when I find a derivative, it's got to be in terms of an independent variable, which in this case is defined as x, of the functions of x. Right, so again, if I want to find that derivative, we're going to practice our notation. Please see that they didn't call this y, they didn't call this fx. So because this wasn't defined as y or fx, I'm going to have to go and use the notation saying it's the derivative of x squared in terms of x. So I'm just using that notation that I've already discussed. And now we're going to use our differentiation law or rules. Our differentiation rules say take the 2, multiply by the 2. So I multiply by the 2. Keep the x and then make that exponent 1 less. So 2 minus 1 is 1, which means the derivative of that particular function is 2x to the power of 1. Very simple, very straightforward. Now, I know there is another way you could do this notation, just by the way, and some people do like to do it like this. So instead of using that d over dx notation, you could go and say, let me set that function equal to y. And then you could actually go and say, but because it's now defined as y, it's dy over dx, which is equal to 2x. So yes, people, that is an option. That's definitely an option, but we'll continue with practicing the different notations. Now there again, they want us to find the derivative of x to the power of 3. So I'm going to say it's the derivative of x to the power of 3 in terms of x, which is my independent variable. And that is going to be equal to, take the 3, multiply there, so it's 3 times x, and then make that exponent 1 less. It's always 1 less. So 3 minus 1, making it 1 less, is 2. So the derivative of x cubed in terms of x is 3x squared. And that's just how you employ these rules of differentiation. Now the next one, also in the textbook, example 3 on page 202. It says, please find the derivative in terms of x to the power of negative 4. Now again, I'm going to write that notation, the derivative of x to the power of negative 4 in terms of x. There we go. Now, just because the exponent is negative doesn't change anything. I'm going to use that exact same rule which says we multiply negative 4, which is my exponent, by x. There you go. And then I make that exponent 1 less. Now careful here, because a lot of people, they make this mistake the first time they do it. I need to make negative 4 1 less. So it's minus 4 minus 1, which is minus 5. So the derivative of x to the power of negative 4 is negative 4 x to the power of negative 5, because minus 4 minus 1 is minus 5. So please watch out for these negative exponents. Okay, we're going to keep going with these examples. Next one, example 4 on page 202. Find the derivative of 3x squared. Now, this particular one is one of those ones where I said we now have a k value or a coefficient. Sorry, there's technical difficulty. Sorry about that. We now have a coefficient other than 1 in front of x squared, which is 3. So I'm going to say I want to find the derivative of that 3x squared in terms of x. And like I discussed, we're going to take the 2, that exponent over there, and we're going to multiply it by the 3. So we're going to go 2 times 3 is 6. And then I'm going to write the x down, and I'm going to make that exponent 1 less, and 1 less is 2 minus 1, which is 1. So the derivative of 3x squared in terms of x is equal to 6x. So that is the derivative if you have that coefficient which is not 1 in front of it. Okay, so we keep going with these examples. Next one. Again, I want to find, and by the way, let's practice one of the other notations just for a change. So I want to find the derivative of that minus 3x to the power of negative 4 over 4, and I want to find that in terms of x. So that's also a valid notation saying the derivative of that particular function in terms of x. Now in order to do this one, you need to be a little bit careful. You need to understand that that entire minus 3 over 4, that whole thing, minus 3 over 4 is my coefficient. So because minus 3 over 4 is the coefficient, I'm going to have to multiply negative 4, and I'll write it out like this, negative 4, and I'll even put it over 1 to make it easier to see. So negative 4 over 1, which is the exponent, must be multiplied by the entire coefficient, which is negative 3 over 4. And then I've got x, and again, I want to make that exponent 1 less. So I want to say minus 4 minus 1 is minus 5. And then just to simplify, you'll notice the negative and the negative multiplied by each other gives you a positive, and obviously the 4 divides into the 4, so I end up with 3x to the power of negative 5. So please watch out for those fractional coefficients. So even if it's a fraction, you're still going to go and multiply whatever that exponent is by the coefficient and make that exponent 1 less. Good. By the way, obviously if I'm going too fast, you can slow it down by just pausing the video, but I'm trying to get as many of these done as possible just so you can get into the habit of using these differentiation rules. Because again, very important, they always ask questions on the differentiation rules. And more important than that is you're going to have to find the derivatives of functions to use later on, to use in graphs. And because you need to use that in graphs and also later in something called minimum and maximum problems, you really need to be able to find the derivatives using the rules. Now this one, you'll see if you look in the textbook, example 5 on page 203. I've changed it to say y is equal to, just so I can practice some of the other notations instead of just practicing that that notation of d over dx of the function. So I've set this one equal to y, and because it's equal to y, I can now go and I can say the derivative of the function y in terms of x. Now this is the first one that has multiple terms, and just because it has multiple terms does not mean it's going to be more difficult. It's actually very simple. There is an additional rule that says as long as I'm adding these terms or subtracting them in this case, so as long as they are separate terms, in this case 1, 2, 3, 4 terms, I can find the derivative of each term separately using those differentiation rules. So I will take the first term, 3x to the power of 4, and I will take the exponent 4 times 3, which is 12, x to the power of 4 minus 1, make that exponent 1 less, which is 3. So that's the first term. Then I will just move on to the second term, and I will repeat that process, saying 2 times 2, which is 4, x to the power of, make that exponent 1 less, so 2 minus 1 is 1. Then over there, that might be a little bit tricky because we haven't done one like this before, but there's always a little 1 there, which is the exponent of x. So we go 1 times negative 5 is negative 5. And then we make that exponent 1 less. Now I'm going to write it out. You don't actually have to write it out, but just I want you to see what happens here. So if I write down x, we say 1 minus 1 is 0. So because 1 minus 1 is 0, if I make that exponent 1 less, I get an exponent of 0. And you should hopefully know x to the power of 0 is equal to 1. And we'll finish that up in the next step. Now be very careful because this is also the first time we've done this particular one. The derivative of a constant, people, is 0. So I can put plus 0 there, but again, it's not necessary, but you have to remember, if I find the derivative of a constant, it's equal to 0. So I'm going to clean this up, and I'm going to say it's 12x to the power of 3 plus 4x minus 5, because obviously x to the power of 0 is 1, so 5 times 1 is negative 5. So that is the derivative of that particular function. And you can always check whether you're doing the derivatives correctly, because if the function has a degree of 4, so remember the degree is the highest exponent of x, then the derivative of the function, because I make all of these exponents 1 less, is going to be x to the power of 3. So you'll know that you've got this right. Next example. Now, this example has got some more complicated exponents, and some of you are going to struggle a little bit with more complicated exponents just because your exponents aren't necessarily as good as they should be. But that's okay. Let's go. So I changed again the function, and I said I've defined the function as fx, so I can practice that particular notation. So I say the derivative of fx, and specifically the first derivative, is equal to. Now here I've got minus a quarter times a half, so I'm going to write that out. Minus a quarter, which is my exponent, times a half. And then I'm going to write down x to the power of, and this, a lot of you might find a little bit tricky, because I now need to go, what's minus a quarter? And I'm going to write it over here. What's minus a quarter minus 1? So minus a quarter minus 1 is then going to be minus a quarter minus 4 over 4. Which then gives me minus 5 over 4. So that means this exponent, if I make that 1 less, is minus 5 over 4. And again, people, if you are struggling with these, you can always go and you can use your calculator. So you can always go and you can say, I've got minus a quarter, and I want to subtract 1. So minus a quarter minus 1 is then minus 5 over 4. And that's then the new exponent over there. So in the next one, I'm going to say it's minus a third, which is my exponent. So I take the third, multiplied by the 6, and then x to the power of a third minus 1. And a third minus 1, either by using your calculator or by doing it rough somewhere on the page, you're going to say a third minus 1 is then negative 2 over 3. Now, this one, please, 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 people, be careful. Pi. Pi is not a variable. Pi is a constant. Pi is equal to 3,14 if I round it off. And we have discussed this already. The derivative of a constant is 0. So I'm not even going to write that 0, but please remember the derivative of pi is 0. So I'm going to clean this up, and I'm going to say this is minus 1 over 8, x to the power of negative 5 over 4, minus, and then obviously if I put this over 1, 3 goes into 6 twice, so that's going to be 2x to the power of negative 2 over 3. Now we'll discuss these negative exponents in a later video, but when we discuss these negative exponents, for now you can just leave the answer as a negative exponent, practicing these particular ones. Okay, some more examples. Now, these are particular examples you have to be careful, because this is not written in the same manner that the previous ones were written. In other words, they aren't separate terms. And that is why whenever you encounter these ones, you've got to go and first simplify the algebra. Now, please look at my notation very carefully. I'm going to multiply this out, and I'm going to go and say it's 2x squared. So that's my 2x squared plus x minus 6x, which is minus 5x, minus 3. Now I can find the derivative. Now look at my notation. I didn't say this is dy over dx. This is not dy over dx. I haven't employed the differentiation rules here. This is still y. So please, people, do not write dy over dx until you use the actual rules. Now I can say dy over dx is going to be equal to 4x minus 5, and that, the derivative of a constant, is 0. Now, I will record the rest of these examples in a separate video because this video is running a little bit too long. So I will call it the extension on notation and the differentiation rules. So you can also watch that video to see the next example.